Hey guys, welcome to our video on the ionization of water and an introduction to the pH scale. In this video we'll be going through the autoionization of water, introducing the pH scale, and linking this autoionization of water to the pH scale itself. Before we start, it's pretty important you have a pretty sound understanding of the autoionization of water. This is a concept developed by Bronsted and Lowry in 1923. This was a time of big discoveries in science. I think Rutherford had just discovered the electron, and this came pretty soon after. They theorized that if we had a beaker of water, all of those H2O molecules were not independent of each other, and they would actually, in the right circumstances, self-react with one another. I'll show you exactly how, and I think it's pretty important for you to understand the chemistry behind this. So these are two water molecules that I have made earlier. So we have two electron pairs on this oxygen. This would give oxygen a slight negative charge and the hydrogens a slight positive charge. We have a neighboring water molecule, same here. The negative charge on this oxygen would start to attract the positive charge on this hydrogen. In turn, this would create this structure, which we know as hydronium, or H2O plus, or H plus. So basically this is an example of a coordinate covalent bond happening. And that might be a term you're not familiar with, so I'll explain that now. In the original water molecule, the oxygen and the hydrogen were both donating electrons towards the bond. Hydrogen donating this one, oxygen donating another one. In this, so hydronium for example, oxygen gives both of its electrons to hydrogen, so it can now bond and make this bond. Obviously, this water has had its hydrogen ripped off, so we have OH minus left. So we have two products left, OH minus and H3O plus. Now we'll build on that with three very high order associations. The first of which is the dissociation for pure water at 25 degrees Celsius being 10 to the power of minus 14. This was found experimentally, and that's something that's pretty important for you to know. The dissociation constant, which you would have known from other videos, is how well a substance likes to dissociate in a solution. For water, this is very low. So it's pretty self-explanatory. Water doesn't like to dissociate in solution. From the equation, H2O plus H2O reacts to form hydronium and hydroxide in a reversible manner. We can see that hydronium and hydroxide are present in a 1-to-1 molar ratio. So for every 1 mole of hydronium, you have 1 mole of hydroxide. We'll refer back to that first point. That 10 to the minus 14 goes to show that that second reaction in the dot point doesn't happen often. But when it does happen, hydronium and hydroxide are present in equal amounts. Also, water is a pure liquid, so we can assume that the concentration of water is exactly 1. I think for me at least it was pretty important to understand what I was memorizing, especially when it came to formulas, instead of bulk memorizing formulas. So I'll take you through a very important association that you're going to want to know. The first thing here, we have the formula for the dissociation constant. Unfortunately, I'll backtrack and say that's just something you're going to have to memorize. So we have this here. Now we have the equation we've been dealing with this whole time. So water plus water reacts to form hydronium and a hydroxide in a reversible manner. So we'll just go on and sub that in. Another thing I wanted you to note is the format. It's very important that you have your formula and your substitutions all underneath, because you do get marks based on your formula. So when we sub that in, we get this here. If you flick back to the previous page, there were three very important things I wanted you to remember. The first, that the Kw we found experimentally to be 10 to the power of minus 14, and the concentration of water being 1. So if all of this is all over 1, it would be nothing but Kw equals the concentration of H3O times the concentration of OH minus, which is exactly what we have here. But as I said, we remember that Kw equals 10 to the power of minus 14. So we have H3O times OH minus equals 10 to the power of minus 14. And I should say the concentration of H3O times the concentration of OH minus. However, we remember that the concentration of H3O actually equals OH minus. And I'll just re-jog your memory. That's because these two are in a 1-to-1 molar ratio. Therefore, if these two things are alike, the concentration of H3O squared equals 10 to the power of minus 14. If you put that in your calculator, you'll find that the concentration of H3O equals 10 to the power of minus 7. From this, if this is equal to 10 to the power of minus 7, this is also equal to 10 to the power of minus 7. Thus, in a solution of pure water at 25 degrees, the concentration of hydronium is 10 to the power of minus 7 moles, and the concentration of hydroxide is also 10 to the power of minus 7 moles. Now I want you to remember that association involving hydronium's concentration in pure water equaling 10 to the power of minus 7, but we're going to quickly segue to the pH scale, and we'll come back to that and combine the two concepts. Something you'll see tossed around a lot, or a term that you'll see a lot, is a logarithmic scale. And the pH scale is an example of a logarithmic scale. A logarithmic scale is basically a non-linear scale with a base. In this case, that's the example of a base, reflects the increments at which the scale goes up. I'll bring your attention to the graph I've made on the right hand side. If you see, so the pH value at 14 all the way to 2 reflects a very, very wide range of H plus concentrations. It kind of, after about, I want to say this point, there's a big exponential increase. This whole thing is quite exponential. So thus, we kind of need a scale that reflects that. So if we were to classify pHs just based on H plus concentration, it would get very confusing and it would just be useless. Like saying something has a pH concentration of 10 to the power of minus 7 or 10 to the power of minus 14 or 1.2 times 10 to the power of minus 5 would just be completely pointless. Thus, we need something that reflects the minute concentrations of ions in solutions. Thus, we have a logarithmic scale with base 10. So this formula is something that you're really going to want to memorize. That's a very high order association. One question I had was, why is there a negative at the front? Usually when you see logs, they're a positive log. This is because of the minute concentration. So 10 to the power of minus 5, 10 to the power of minus 7, 10 to the power of minus 14. So the concentration of H plus in this solution will always be something small. So we need a negative logarithmic scale. So now we'll combine these two concepts that we've learned. The first association that we made is that the concentration of hydronium, so H3O plus, in pure water is 10 to the power of minus 7 moles per liter. The second association we made was that to figure out the pH, we put it into this equation, negative log base 10, concentration of H plus. One thing I want you to remember, especially for your exams, is this is a really high yield point. When you're putting it into your calculator, make sure you have log base 10. Log base E will give you a completely different answer, and this will just help you avoid a lot of trouble. So now if we put 10 to the power of minus 7 into our equation, because this is just the same as that. That's something I want you to remember. H plus and H3O plus are used interchangeably. So if the concentration of H3O plus is 10 to the power of minus 7, we can put that into our equation to figure out the pH. So we get something that like this. Again, notice the layout. It's very important that you show equation, substitution, and then answer. Speaking of which, if you put this into your calculator, you'll get a pH of 7. Thus, the pH of pure water at 25 degrees is 7, which is a neutral pH. That's actually how we figured out the neutral pH, and we base all our pHs around this. Next up, we have a quick module on how to actually use the pH equation in answering questions and figuring out the pH of different solutions. But before that, I want you to remember these very 4 high-yield dot points from this video. The first, water can self-ionize in solution. You learn the chemistry behind it and the concentration of H3O plus in a pure water solution at 25 degrees being 10 to the power of minus 7. This is something that's very important. So that's just a step before how we got to 10 to the power of minus 7, but I want you to know this. The pH is a logarithmic scale with 10 as the base, and this is the equation for how to work out the pH of a solution.